Hey guys, let's do our electromagnetic spectrum drawing. Alright, so to save time, let's follow, or I'll tell you about the directions. We're basically going to take this chart on the front of the paper. We're going to use the numbers that they gave us to fill out this part on the back. So I'm going to take off my questions just because I'm flipping a lot, so get rid of those. Okay, so as we look at the front, let's talk about what we see on this page. So I see things that look like stuff I've heard before. So I see just an M. I see CM, an MM. So think about what those mean. So if we're talking about a wave's length, this is something that we're already comfortable with. So let's say we have a wave, and we want to measure from one top point to the other. That's the wavelength. Awesome, right? It's the length between two waves, or between a wave, the length of a wave. So just like you measure the length of a book, this is going to be the same thing. So when we talk about wavelength, we're going to use meters. So we're a little bit comfortable with that. So we're talking in terms of the metric system, our base 10 system. All right, so let's start right here. I see an NM, so that's going to be a nanometer. I'm not going to write all these out. I just want to go over them with you. And then we've got nanometers all the way down until we get to, what is that, infrared? And that's a millimeter. CM is our centimeter. And then we've got centimeters up to 10 meters. And then again, we have meter from that point on. So we have nano, milli, centi, and just a regular meter. So some waves can be up to 10 meters or longer. So that would be the height of some buildings. So just pay attention to your prefixes and let that kind of guide you for what these waves might look like. Okay, so I'm going to let this chart show so that you guys don't have to flip back and forth. You can just work on your spectrum. All right, so I'm going to start on the bottom, and I'm going to use a wide highlighter so that you're able to see where I'm drawing these sections at. So the first thing is going to be long waves, and they go from 10 meters to longer. So let's kind of get an idea of what our picture is going to look like. So if we start on wavelength right here, this is the section of the chart that we're looking at. Don't worry about this frequency yet. I know those numbers have exponents, but I think you guys as 8th graders have had that enough that you're comfortable with what those mean too, and we will talk about it more also. So for long waves, they're going to start at 10 meters and be larger. So let's look at our scale. Up here on the right side, we're in nanometers, millimeters, centimeters, and then meters up to 1,000 meters. So let's start on this end with our long waves. So we're going to put a line at 10 meters, and it's nice. There's already one there for us. And so from 10 meters bigger, it's going to be what kind of wave? I'm going to assume you guys all said the correct answer. That's what I get to do when I'm making these videos. I just assume you're right there with me and you're having just a good time. All right, so those are our long waves, 10 meters and longer. Moving up to the next one, radio and TV waves. They're going to go from 30 centimeters up to 10 meters. So we have our 10 meter mark. So if we start moving to the right, we're getting smaller and smaller. We don't want to come to here because that's 10 centimeters. So they've put us this nice line here, right there, for our radio waves. So this is cool. Let's pause and take a look at this. So think about your favorite radio station. What's the name of it? It might be 1029. So that would go where? Right here. 1029 The Buzz. 1059. Maybe you want to listen to some 98.5. That's going to be right here. So you can fill in your favorite radio station and it would be right there. So I'm sorry, I'm going to ruin a little bit of music for you, but that actual number of the radio station is its actual frequency of the wavelength of that stuff being accepted by the radio station. So mark your favorite station up here on the top. All right, let's keep going. So we've got radio waves. Moving up to microwaves, we're going to go from the 30 centimeter mark. I'm just going to put 30 centimeters there so I remember, up to 1 millimeter. So 1 millimeter is going to be right there. So I'm going to put my line here. And that whole section will be for micro waves. Moving on, 750 nanometers to 1 millimeter. it goes ahead and gives us another line. So if this is 1,000, then we have a nice little line here that's for 750. So let me see if I can just make a skinny line there. Put it on that side so you guys can see it. So this is going to be our infrared. I-N-F-R-A. Infrared waves in that section. Then what do we break out and do? Yeah, we're going to talk about the visible light spectrum. So I'm going to turn my paper sideways and I'm going to write visible right there. All right, so visible light. And then we're going to go break down the visible light spectrum. So I'm going to get my papers a little closer so you can see. All right, so let's look right here. Red, we're going to start at 620 to 750. So you're going to have to just estimate. So 650, we're right here. Then we want to move a little bit closer. So that will be our 620 mark. And that's going to be, I'm going to lightly label that red. 590 to 620, so right before the 600 will be our orange. 570 will be yellow. About 495, so if this is 500, our 495 is going to be right there beside it. That'll be green. 450 right in the middle for blue. And let's see, 450, so 420. Our indigo, because we all know the difference between indigo and violet. It says no person ever. And then 380 is going to be our violet. So you guys can go back later and add some color to that. All right, so we'll move up to UV. So we're going to go from 400 nanometers to 10 nanometers. So here's about our 400, and then here's our 10 nanometers. So we'll draw that line again. That'll be our UV light. And then X-ray is going to stop at 0.1. It's already got us a little line there. So here are X-rays and gamma at the end. Okay, so we've got it labeled. So take a second and pause the video and color. I'm just going to throw a little bit to it because I don't know how to pause my video and then restart it. Uh-oh, my red and orange look the same. All right, so I want to see you guys do a better job coloring than I did. It's a rush job right there. All right, beside it, let's write down what these colors are. So we said Roy G. Biv. Roy G. Biv, so that you can remember the order. And one trick that I use is to remember that your red is on the radio wave side. So stick those R's together, and that'll help you remember which way those waves go, because that'll be what we talk about on our Friday quiz. So if you were to lay this out and you were to have radio waves, whatever side radio waves are on, that's where the red end of your visible spectrum is. So red and radio are always going to be together. So if they give you just this part and you don't know where visible goes, find radio waves, and then the red end of the visible spectrum is on that side. So that's about the only trick for you that I have. So let's talk about this visible light spectrum and where the most energy would be. So if you've got a line, well, let's hold on because I want to go back and draw the wave. So if you look at mine, I messed up on it before, but here's what we're going to do. So radio waves are really long, so I want to draw a line through here to kind of show you what they start to do and how they start to get closer and closer and closer together. So that's our goal. So I'm going to start out pretty big on the long wave side, obviously because they're longer waves. And then about the time I get to infrared, and then gamma Oh, that needs to be really close together. Okay. Obviously, this is nowhere near any kind of scale, but the whole goal is that we start out wide and we start to get our waves closer together. Okay, I did a terrible job on that. So let's go summarize a little bit of what we've done. This is our visible light. Now that you have your waves and you can see a little bit of how energetic they are, where on your visible light spectrum do you have the most energy? Well, the closer the waves are going to be, like from crest to crest, all of these points, they're very close. So there's going to be more energy there. So this is the more energy side of visible light, and this is your less energy. So let's describe the waves that we have on this end. So if we take gamma rays and we're going to come down here, what kind of wavelength do they have compared to their frequency? So you've all seen, I'm going to rewrite this one because I'm just going to talk about it. So 10 to the 19th, what's that going to mean? A 10 and 19 zeros, right? And so if you look at the other side, we've got 10 to the 6th. So if you were to write those numbers out, you would see they're significantly different, right? So this has a higher frequency. Frequency means just how many times something's going to happen. So how often you have science homework. That can be an example of frequency. And then on this end, we have a lower frequency. When we talk about frequency for waves, we want to know how many waves can go by in 1 second. So that's typically our time frame is just 1 second, how many waves went by. So if you've got a really long wave, you might only get half of a wave by you in 1 second. Where if you have a gamma ray, you may have hundreds or thousands of waves go by in a second. So these are definitely our more energetic. So on the gamma ray side, I'm writing more energetic. And we can't say these words enough. So we're going to say a higher frequency. You can abbreviate. But what did the wavelength do? Is the wavelength further apart from crest to crest? Or is the wavelength closer together? Wavelengths closer together, so the number for wavelength is going to be smaller. So with a higher frequency, you're going to have a smaller wavelength. And then when that happens, you definitely have a more energetic wave. Excellent. Y'all are doing fantastic. All right, let's go up. I'm going to switch my hot watercolor as we talk about frequency. And we said frequency was the number of waves per, remember our little line for per second. So how many waves you have per second. That will tell you frequency measured in hertz. Hertz is H-E-R-T-Z. You know Miss Kirby loves her units of measurement. Gotta get all those right. All right, let's move to the other end. Let's kind of summarize what's going on down here. So we have a long, what do we have? We have a longer frequency. So if we're going from trough to trough, look how much space there was before you even had another wave. Of course, that's not accurate, but that does show you that the wavelength here is much further apart compared to the wavelength down here. So on this side, when we have long waves, we're going to say less energetic. Because they have a higher, nope, I'm so sorry guys. They have a lower frequency. So lower frequency, that means in 1 second, you're going to have less of these waves roll past you. And with that though, with a lower frequency, you're spreading out the wavelength. So you have a higher wavelength. So wavelength and frequency are inversely proportionate. If you increase one, you're going to decrease the other. And with that becomes less energetic waves. So really highlight that, because I want you guys on your Friday quiz to be able to tell me which part of the spectrum is going to be more energetic. So if I were to say microwaves and UV rays, which ones are more energetic? You would say UV. If I said orange and blue, which is more energetic? You would say blue. All right. And of course, I'm going to ask you about wavelength and frequency and how they change. All right. So let's move up to the top. Take a quick note on UV, X-rays, and gamma rays. So the reason we put sunscreen on when we go outside is because any of those rays or waves will kill living tissue. So channel your information from last year when we said cells make tissues, tissues make organs. Those cells are living, cells make up tissues. Those cells have DNA in them that make up bigger parts, you know, called tissue, and we can kill those cells and the DNA in them with UV, X-ray, and gamma rays. It will break down. Any of those can break down DNA. And those three types of waves have so much energy that they can break apart or they can break electrons away from their atoms. I don't know about you guys, but I'm not that powerful. So X-rays, UV rays, and gamma rays kill living tissue. They break down the DNA inside the cell, so that's the problem. And if they don't necessarily kill it, they can damage the DNA so much that it doesn't perform its normal job. So we said all cells are made to have certain jobs. They have specialized functions that they perform. So if those cells even if they don't get killed by these rays, then they might become damaged and they're not able to perform their function. So they break down DNA, and they have so much energy in them, they can break electrons away from their atoms. That's a big deal. Okay, so that's that part. Let's move on to the questions. So when you start to answer these questions, I want you to answer these questions on your own. Do not just let this video roll on through and you guys sit there and write your answers. Okay, not cool. So let's see how to get started. Let me just give you a few tips before you pause your video. Let's look at number one. I'm going to talk you through a little bit of it. An atom emits a wavelength of 449 nanometers. What color light? So that's just coming back to your chart and finding that. When you look at number two, you're going to look for 10 to the 16th power. Okay? So I'm going to pause, or you guys pause. I'm not going to pause. I'm going to keep going. So you guys pause the video, answer your questions, and then jump back on, and I'll walk you through them. All right, so number one, when we walked you through it, what's my answer key? I want to make sure I don't mess up. Here we go. All right, Kirby set. So 449 nanometers, that means you guys are looking at the color indigo. So tell me about indigo. Does it have a high frequency? Is it very energetic? Yes. So it didn't ask you. I know it didn't. But I want you to tell me that that's very energetic. Okay? I'm very tempted to even have you say a higher frequency and a smaller wavelength than red, but we won't. Okay, so 10 to the 16th, if you check your scale, it wants to know if we can see that. So that means visible with our own lines, or own eyes. So when I see 10 to the 16th, what section does that put me in? Ultraviolet. And even though that is next to the visible light spectrum, my old eyes cannot see it, and neither can your young ones. So no, because 10 to the 16th is ultraviolet. All right, number three. A beam of electromagnetic radiation has a wavelength of 1 meter. What part of the spectrum is that beam from? On our scale, we're going to find 1 meter. That puts us in the radio wave section. So we're in the radio wave section, and that has a range of Oh, what is radio wave? 10 meters. All the way down to 30 centimeters. So that's a pretty wide range. All right, we're going to rank these from the highest amount of energy. So start with your most energetic wave. It's not asking for all of them. It's just giving you a few choices. So looking at your chart, you're going to start with X-ray, UV ray, then we go to violet, yellow, red, and then radio. So highest energy. So this is our most energetic to our least energetic. So we're going to rank these 10 to the 16th. So when I look at that, what's its wavelength? 10 to the 16th. That's about, I don't know, what do you say? 50 nanometers? Oops, I messed that up. 50 nanometer. And then what were we looking at if we looked at that? 10 to the 16th was going to be what? 10 to the 16th was UV. So I want us to write that out to the side, even if you didn't before. Now we have a wavelength of 1 centimeter. So what's that frequency going to be? So let's find 1 centimeter. That frequency is going to be about right here. So let's just say 1 to the 10th, or 10 to the 10th power. 10 to the 10th hertz. And we're talking about micro waves. We have 100 nanometers. So 100 nanometers puts us back at 10 to the 16th, and we're still in the UV, but we've moved down a little bit. I'm going to mark that just a little so we come back to that. 10 to the 16th. And that was UV, wasn't it? 10 to the 13th. Right in the middle of infrared. Oh, that wasn't the question, was it? I didn't look at the wavelength. For 10 to the 13th, what? That's about 50. I love this symbol. Okay, so watch. You're going to make a backwards Y. Cool, huh? That's for nanometer. And then 10 to the 15th. 10 to the 15th is what? About 100? Nanometer, and 10 to the 15th, we're rocking visible light. All right, so let's move these. It wants to go from hottest to coldest using their frequency. So when we rank these, we're going to start at the top. So we're going to come over here to the side. I'm going to say hottest, and we're going to go from A. C and E are actually going to be the same, and then D and B. Okay, Kirby's going to take a pause. Right here, a timeout. We're going to talk about some metric stuff. So this isn't part of it, and if you don't have room, you can work this at the bottom of your paper. So you can have a tera, T-E-R-A. So you guys have probably heard of like a terabyte for a computer, method of storage. So a byte would be a method of storage. You can have a terameter, and that's going to be anything 10 to the 12th. A gigameter, 10 to the 9th. A megameter, 10 to the 6th. Kilo, so we're getting comfortable with these because that means 1,000. So if you said a kilometer, that'd be 1,000 meters, and kilo is going to be 10 to the 3rd. Milli. That's going to be 10 to the negative 3rd. So that doesn't mean we go negative. That just means if the decimal point's here, we're going to move it this way and make the number smaller. You can have a micro. So we've heard that today. And that's that really cool symbol of the backwards Y. So a micrometer is 10 to the negative 6th. I'm going to run out of space. There's 2 more. A nanometer. Just use an N, 10 to the negative 9. And see if you can put one more on there. This one's fun. A picometer. A picometer, just with a P. is 10 to the negative 12th. I hope you were able to fit that on your paper. So that's kind of neat to see. 6 units to the right of the decimal, 9 and 12 units were getting really small. Okay, moving back. Number 6. What general range of waves are more dangerous to your skin? All right, so we put that on the front, more dangerous to your skin. High frequency or low frequency. So if we look back, what did we say the kind of waves were that were dangerous? UV, X-ray, gamma wave. So what kind of frequency did they have? Higher frequency waves are more dangerous. So we're going to say higher. Higher frequency can, I want you to repeat it. I know you wrote it on the front. Can kill living tissue and DNA. Okay, number 7. Atoms that are energized give off many separate colors, but not the whole rainbow of colors. So why is the number of colors limited to a specific set? So let's go to atoms. And you guys just finished the star spectra gizmo. So what we wanted to take away from the star spectra gizmo is that each element emits its own color. So we're going to start with that. And why is it limited to a specific set? So we're going to answer all of that. So each element will emit and absorb, because we saw the absorption spectrum. That was the part of the spectrum that was black, because that was what the star was absorbing. So each element emits or absorbs its own color based on its amount of energy and wavelength. And we're going to put a reminder in there to remember the star spectra gizmo. All right, so why do they give off more than one color? So I think that's a sub-question of number 7. So it could be due to a combination of elements. So you saw one had magnesium and iron. You saw another one had helium and hydrogen. And it took both of those absorption spectrums to line up with the absorption lines from the star. So because it's a combination of elements. And you can have shifting electrons. So shifting electrons within atoms will cause a difference in color and a combination of elements. So you know the mnemonic device for Roy G. Biv. We've talked about that for the visible light spectrum. Now we're going to make our own. So if you just go Google, you can type in mnemonic device for electromagnetic spectrum. And I'm just going to tell you the one that all the kids remember. So we're starting with radio. Oh, no, I'm going to mess up. So you Google and you find your own, but the one we say is rabbit's mate in very unusual, expensive gardens. So underneath that, I'm going to turn a little bit and I'm going to say gamma. All right, so whatever helps you remember it. I can put that right there so you can see everything. Rabbits mate in very unusual, expensive gardens. All right, so study this for your quiz. I would keep this last part in mind, and good luck.